Okay, before we get too far into all of the U substitution techniques that we're going to be looking at in sections 5.5, 5.7, and 5.8, I want to pause for a moment and talk about how U substitution is going to affect a definite integral where we're calculating net change as opposed to doing the indefinite integrals where we're calculating a general antiderivative. So what we're going to do, there's really not a lot to this section. This is going to be a fairly short video, but there are two methods that we're going to be doing in order to do this definite integral using a U substitution. And one of them is going to be a little bit shorter and will probably be the one that we use more often, but you have to be very, very careful when you are doing definite integrals and U substitution, because you can get into trouble if you don't pay attention to what you're doing. And let's talk about it by just looking at an example where we're going to do two different methods for evaluating the definite integral and calculating your net change. So the first thing is to recognize, oh hey, the definite part of this, knowing that you're going to get an actual numeric answer, that is the net change, is one thing to pay attention to, but the first part of this is very similar to what we would do for an indefinite integral. I am going to need to calculate an antiderivative of this, and the only way to take the integral in this form is to do a U substitution. So we recognize that we're going to have to make the U be what's underneath of the radical, and if I let U equal 1 minus 4x cubed, I see that its derivative would be negative 12x squared dx, and so I see that the stuff on the outside is really close to the derivative of u, and the only thing I'm missing is pretty much a constant that I'm going to need a negative 6. So, and we can always correct for the negative 6 that's missing by putting it in. So I'm just going to bring everything down, kind of rewriting it so that we can clearly see what we're doing. And so I am going to put in the negative 6 constant that's missing and then correct for it on the outside. So that's standard, same antiderivative steps that we were doing for U substitution. Now, as I continue to do this problem, remember that what we're doing is all the stuff on the outside is now going to get packed back up into this box. And so I'm thinking of this as when I do the antiderivative, I'm basically doing the antiderivative of u to the 1/2, because the rest of this stuff gets packed back up because of chain rule. So the antiderivative of u to the 1/2 is going to be the u, add 1 to the power, 3/2, and then divide by the power, which is the same as multiplying by 2/3. Now at this point, if we were doing an indefinite integral, I would be doing plus c here. But I'm not doing an indefinite integral, I'm doing a definite integral, and I'm calculating net change. So I show that I'm going to evaluate this at negative 2 and 0 so that we see that we are doing net change. And then from that point, it's simply your plug and chug with your arithmetic. You're going to plug in your 0, and we're going to end up with negative 1/9 times when I plug in 0, I'm going to get 1 to the 3/2 or 1, minus, then I plug in my negative 2. You're still going to get your negative 1/9, and then when I plug in my negative 2, I get negative 8 times negative 4, which is positive 32. 33, so I now have 33 to the 3/2. And you know, this is not a nice number, but that's okay. It doesn't really matter. Our final answer, negative 1/9 plus 1/9 times 33 to the 3/2. It's not a rational number, so I'm just going to leave it in this form. So now a couple of things to notice as we went through this problem. At the beginning of the problem, we need to recognize that we have bounds, that this is a definite integral. Even though I start doing this kind of in the same process when I would do an indefinite integral, I'm going to tell you that what starts as a definite integral better be a definite integral all the way through the problem, or you're going to lose your math communication points. So if there are bounds here, there better be bounds here. After you get your general antiderivative, you have to show that you know you're still doing a definite integral, and then you calculate what your actual net change is. So that's going to be the first thing that you have to be very careful of. If it starts as a definite integral, it better be a definite integral all the way down until you actually evaluate the definite integral. Now, method 2 here, okay, so we're going to contrast this with the second method. Just make that darker there. And the second method has to do with kind of in this step that I still kind of do the same thing when I get to here. I'm going to have my negative 1/6. So it actually doesn't really start being different until I get to the next step. This is my integral, -2 to 0. I add the -6 in, just like we did before, times the 2x squared, square root of 1 minus 4x cubed dx. Now remember that sometimes when you are calculating these integrals, that one of the methods was you could actually do the u substitution. Sometimes you can see it without doing the u substitution, but sometimes we do want to go ahead and put the u substitution in. So we recognize that the -6 times 2x squared dx is going to become my du. That this right here is u to the 1/2, and we bring our constant down. So this is me actually performing the u substitution. Now here's where you have to be very, very careful, okay? If I perform this u substitution, remember I said that if it starts as a definite integral, every step has to be a definite integral. And so I had my bounds here, but notice that when I got to here, I no longer have bounds. And so I need to adjust for that. But be very careful. Do not just bring your 0 and your -2 down and write them here as bounds, because these are your bounds. These are x values that you are plugging in. When you change everything into terms of u, you have to change your bounds as well. So we're using, to figure out what our bounds are, this little formula that we have up there. U is 1 minus 4x cubed. So you have to figure out that if this is my x, what's the u that I would have? So when x is -2, u is going to be 1 minus 4 times -2 cubed. This is going to give me my 33, okay? So that's your 33. And then when x is equal to 0, your u is going to be 1. And that would give me 1. So when you write your bounds down, if you switch to u, you must change your bounds to u. That's where you have to be careful. Now the nice thing about this is that I don't have to go back to x. Like when I integrate this, I'm going to have -1/6, and then we do u to the 3/2, and then our 2/3, and where you go, I'm evaluating 33 to 1. I do not have to go back to x. I can, because it's a definite integral, the net change when it's in terms of u, when u is 33 and 1, is going to be exactly the same net change when I have it in terms of x, and x is -2 and 0. So it actually ends up being easier to just go ahead and put in the u substitution, because you're going to have to calculate. Do you see this 33 is right here? And that the 1 was right here when technically I didn't write it, but times 1 when I calculated that one, that I end up in exactly the same spot. -1/9 times 1 to the 3/2 minus -1/9 times 33 to the 3/2. And it actually, if you look at it, looks much cleaner because you've done the calculations as you go. So the trick is, okay, one thing, and I can't stress this enough, if it starts as a definite integral, it must be a definite integral through the entire problem. If you switch your variable to u using a u substitution, if you actually write u down inside of your integral right here, not only do you have to switch everything inside in terms of u, you have to change your bounds to be in terms of u and show that you're doing a definite integral. All right, so let's look at, we're going to do 4 more examples of this, and then I think that should be enough for you to kind of understand how the definite integrals work. And like I said, the one that I use is because usually revealing the integration using the u substitution, if I'm going to do a definite integral, I pretty much always convert it to u and convert everything to u, and then I don't worry about going back to x, which is a little different than if you were doing a general antiderivative. Your general antiderivative must be in terms of the variable you start with. All right, so here's this one. Notice I don't have an x, I have a w there. Don't let that bother you. I'm going to notice that I have a u substitution. U is going to be 2w plus w squared. We're working on power rules integration. So when u is this, I calculate my du, 2 plus 2w, dw, in your differential form. I notice that I have a 1 plus w out here, so that's close to this one. That's really just missing that constant of a 2. And it's okay to be missing a constant, so I'm going to take this. I'm going to add my constant in, just copying it down just to be thorough so that everybody's following along. So I add my constant in, and I put in my corrector. All right, and a lot of times if I'm doing this, I usually come over here, instead of rewriting this to save myself some time, you'll see me start to do this. And so that will save you the time and you don't have to write it, because if I write this, I also have to write bounds. So let's assume that we kind of squeeze it in, that we're trying to save ourselves some time. Now when I do that, now I'm ready to convert it into terms of u. So I have my 1/2, my integral. I'm going to wait for my bounds, okay, because I'm switching everything to u. The 2, 1 plus w dw is your du. This is where your box is. Okay, again, keeping it in terms of how we were teaching this before. There's your box. So I am going to go ahead and change that to u to the 5th. And so I make that easy to integrate. Now I need to change my bounds. And a lot of times I just kind of down here show my work. When x equals -1, u is going to equal -2 plus 1 or -1. So I fill that in. And when x is equal to 5, u is going to be 10 plus 25 or 35. So I fill in my new bounds. So I am keeping my rule that what starts as a definite integral must continue to be a definite integral. And since I changed into u, I changed everything into u. Now I calculate my antiderivative, u to the 6th divided by 6. And then I'm evaluating it from -1 to 35. I don't worry about going back to x. I don't need to for net change. So I'm essentially going to have my 1/12 times 35 to the 6th minus my 1/12 times -1 to the 6th, which is 1. And so you're done. You have your answer, not a nice number, but good enough for what we're doing. And so there's the idea that what starts as a definite integral must always be a definite integral, and it must be in terms of whatever variable you are using in your integration. If you switch to u, you have to switch your bounds to u. All right, let's look at another example. Okay, for this next example, same idea. Now, does it bother me that I have two subtraction right here? No, I'm going to go ahead and distribute. When I distribute, notice you're going to have two different rules that you're going to use here. In both cases, whether I'm doing this one, which is going to be a power rule problem, or this one, which is going to be a log rule problem, I'm going to let my u be the same thing, 1 plus 2x, so I go ahead and write it down. My du is going to be 2 dx. So I'm going to come across here and I'm going to distribute my integration through. Don't forget to write your bounds, -2 to -6. This 4, I'm going to pull 2 of the 4 out because it's kind of like a writer. And I'm going to leave 2 dx inside. And then this is going to be my 1 plus 2x cubed. I'm going to rewrite it in the next step, minus. The 5 is going to be a writer. We pull it out. And then we have our negative 2 to negative 6. And then we're going to have our 1 over 1 plus 2x dx. So this is just kind of distributing and getting it ready so that I can do my substitution. Now notice that in the second one, this one I pulled 2 out. 2 times 2 is 4. I didn't need a corrector. I have the 2 dx in there. Over here, I need to have a 2 in here. So I put in a 2 and I take out a 2 for my corrector. So that one's ready to go. Now I'm going to pretty much change myself over to u. Here's my du, and this would end up being u to the negative 3 du. Integrate, bring your constant down. I'll do the bounds in a second. Minus 5 halves, my definite integral. This is du over u, or 1 over u du. Now I need to switch my bounds. What starts as a definite integral must be a definite integral in every step. So we're going to have to add these bounds in. And when I add them in, because I've switched to u, I'm going to have to find the bounds in terms of u. So when x equals negative 2, u is going to be negative 3. So I fill that in. And then when x is equal to negative 6, we get negative 12 plus 1, u is negative 11. So I fill that in. Now I'm ready to do my integration. I'm still doing a definite integral, so I've shown I've got definite in every step. I do my power rule, so 2 u to the negative 2, add 1 and divide by negative 2, minus my 5 halves. Now I'm in log rule, natural log, absolute value of u. And notice I didn't put the, hey, I'm doing a definite integral, because it's the same bounds on both of them. So I might as well just wait to the end and do negative 3 to negative 11. So what starts as a definite integral must be a definite integral all the way through the problem. Now I'm just going to do my calculations. I'm going to put in my negative 11, and this is negative 1, so it's negative 1 over negative 11 squared, 121, minus 5 halves, natural log, put in your negative 11, absolute value of it, natural log of 11, minus net change, put in your negative 3 and square it. It's going to give you negative 1 over 9. Let's do a parentheses here. Minus my 5 halves, negative 3, absolute value 3, natural log of 3. And then from there you would simplify your arithmetic, and that's basically just showing you how we do this. All right, couple more examples. All right, here's one for part C. And again, not going to worry so much about our integration. Now the nice thing about this one, I can distribute the integration over addition. So the first one, the 0 to 1/2 e to the y dy, does not have a u substitution. So I just bring it along. Now for the second one, when I go to do this one, I'm going to have to let u equal pi y. So du is going to be pi dy. And so I need a constant in here. The 2 is a writer, so I pull it out. I'm going to have to add in my pi and take it out. Put in your correction. All right, and then you're going to have your cosine of your pi y dy. So I kind of get myself to here. This is 0 to 1/2. What starts as a definite integral has to stay a definite integral. Now this one we can go ahead and integrate. There's nothing to it. The antiderivative of e to the y is e to the y. We're evaluating it from 0 to 1/2. Now over here, if I rewrite this one, I have 2 over pi, my definite integral. I pack up all the stuff. Remember that we have our box that's going to be right here. So we're doing cosine of u as what we're actually trying to integrate. So we pack everything back up and we do cosine of u du. Now I need to change my bounds. When x equals 0, your u is going to equal, I should be doing x. When y is equal to 0, u is going to be pi times 0 or 0, so that stays the same. And when y equals 1/2, my u is going to equal pi over 2. So pi over 2. So notice that the first one, I didn't change anything because there was not a u substitution. We would have e to the 1/2 minus e to the 0, which is 1, plus my 2 over pi. The antiderivative of cosine is sine. And again, I don't need to switch that back. I'm just going to evaluate it from 0 to pi over 2. Now, this is sometimes where you need to be careful that this does not go to both of these. It only goes to this last one right here. So it's e to the 1/2 minus 1, and then we plug in our pi over 2, plus 2 over pi times the sine of pi over 2, which is 1, minus, plug in 0, sine of 0 is 0. So we get our final answer, e to the 1/2 minus 1 plus 2 over pi. So the idea here is sometimes you're going to need to change your bounds on one part of the problem because you're using a u substitution there, but not on the other one. All right, and let's take a look at one last example before we go away. You want to be very careful when you are doing this that when I integrate this, I'm actually going to distribute through. So I'm going to do pi over 3 to 0. I'm actually going to pull this 3 out. Sine of z over 2 dz minus 5 integral pi over 3 to 0 cosine of pi minus z dz. So I separate that first. And now you want to be careful, and this is more of a notation thing. In this problem, I'm going to let u equal z over 2. My du would be 1/2 dz. I see that I'm missing a constant, so I put a 1/2 in, and then I correct for it. So I know that what I'm integrating over here on this side, I'm just working on this, is going to be 6, my definite integral. This gets packed back up, and it becomes sine of u du. Now I need to, in this problem, switch my bounds. So when, let me just fit it in over here, when z equals pi over 3, u is going to be pi over 3 over 2 or pi over 6. And when z equals 0, u is going to be equal to 0. So I do change my bounds. Okay. Now we come over here to the next part. We're going to continue the problem. Minus my 5. Now here, don't use u again. I mean, it's more of a kind of, you've already used it. It stands for z over 2. So if I'm going to use something over here, pick a different letter. Don't get stuck on the u thing. I'll use w. W is pi minus z. dw would be negative dz. Am I missing a constant? Yes, I am. I put my negative in, and I'm going to change that. So we'll fix that down there. And so when I do this and I do my substitution, it's going to be cosine of w dw. And then now I need to change my bounds here. And again, when z is pi over 3, now we're changing it in terms of w. W is going to be pi over 3, pi minus pi over 3, which is 2 pi over 3. And then when z equals 0, w is going to be pi minus 0 or pi. So you'll notice that we ended up with two completely different bounds in this, but it was because I had to do one u substitution over here and a different u substitution, also known as a w substitution, over here. And since I'd already used u, I went ahead and switched my variables. And then when we go to integrate, we go the antiderivative of sine is negative cosine. And we're evaluating this from pi over 6 to 0. And then over here, the antiderivative of cosine is sine. And we're evaluating that from 2 pi over 3 to pi. And then we simply do our plug and chug. So negative 6 cosine of 0 is negative 6 times 1 minus negative 6 times the cosine of pi over 6, which is square root of 3 over 2. So that's your first integral with your net change. And then we do 5 sine of pi, which is 0, minus 5 sine of 2 pi over 3. Sine of 2 pi over 3 is square root of 3 over 2. Okay, so that gets us to there, and then we simplify. Negative 6, we have plus 6 minus 5, so plus square root of 3 over 2, and we get our final answer for our net change. All right, so hopefully this gives you a good idea of how to handle definite integrals when you do a u substitution.